the rational zeros theorem will give us a list of possible rational zeros to start a problem. Well, with us being able to use our graphing calculators to see x-intercepts, this method, I guess this will be useful if I don't have a graphing calculator to see the real zeros, but hey, maybe, I don't know, maybe one day you won't have that graphing calculator. If you don't have a graphing calculator, you're going to have to start with something, right? So the rational zeros theorem will give us those starting points. Like it's going to give us a whole bunch of numbers as a potential rational zeros. And what we have to do is we have to check each of them to see which one is actually a zero, okay? But in this video, I'm going to talk about how to come up with this list of possible zeros using the rational zeros theorem, okay? So let's come up with a list. There are only two things that you should be looking at in a polynomial if you want to come up with this list. And those numbers are your constants. So what I will do is I will go ahead and find all the factors of the constant. Okay, we'll say factors of constant. And we'll call these P. We'll call this P, okay? Factors mean like numbers that divides that number evenly. Like suppose that we have 12. If I ask you to list all the factors of 12, you're going to say 1, 2, 3, 4, 6, and 12. So all these numbers divide 12 evenly. That's what I mean by factors, okay? Some numbers, like some prime numbers, will only have two factors. So if you have 17, the two numbers, factors, will just be 1 and 17. But if you have a composite number, you may have more factors, right? So, but when we say P in the rational zeros theorem, we're just talking about numbers that divides the constant evenly, okay? Another thing that we should look at is the leading coefficient, okay? And we're going to call them Q, okay? Alright guys, I'm going to have to restart this app. It's slowed down on me again. Oh my goodness, where am I now? Okay, I'm back here. So I'll go ahead and highlight the leading coefficient. And we do the same thing. Factors of leading coefficient are called Q, okay? So we need to find a whole bunch of numbers, and maybe just two numbers, that divides our leading coefficient evenly. That's how you come up with P's and Q's. So when you do the rational zeros theorem, we start by finding the P's and Q's, and we find P over Q. That's really all it is. All right, so let's start with some examples over here, okay? So example 5 says, use the rational zeros theorem to list all possible rational zeros of the following. Be sure that no value in your list appear more than once. So if anything repeats, we're just going to write it down twice. So like I said, there are only two numbers that you care about in a polynomial when you're using this method, okay? The number that you care about is the constant, 6. So P's are all the numbers that divide 6 evenly, okay? So what numbers divide 6 evenly? You're always going to have 1. You guys are always going to have 1. Hold on. So I'm going to go ahead and say, but hold on a second. Not just 1, but also negative 1. Isn't that true? 6 can be divided by negative 1 evenly. So what I want you to do is this. I want you to go ahead and put the plus or minus sign and draw a parenthesis like this. So what I mean is any numbers that are going in this parenthesis are factors of 6, but they can be positive or they can be negative, okay? So I'll start with 1. 1 or negative 1 works. 2 can also divide 6 evenly, right? 2. What about 3? Yup. What about 4? Nope. What about 5? Nope. Last number that divides 6 evenly is 6. So these are the numbers that we can divide 6 by with no remainder, right? Remainders of 0. So these are the factors of factors of our constant, and they are our P values. Now let's come up with a list of Q's, okay? And Q's are the numbers that divide the leading coefficient. So what numbers evenly divide 2? Of course, I'm going to have to put the plus or minus sign, but 2 can be divided by 1, and 2 can be divided by 2. Ta-da! I got my P's and Q's. And all I need to do is now create a list that is P over Q. Now, all these numbers are going to be first divided by 1. So I'll do 1 divided by 1, 2 divided by 1, 3 divided by 1, and 6 divided by 1. Okay? But dividing anything by 1 is just itself, isn't it? So what I will have is this. I will have plus or minus 1, 2, 3, and 6. Basically just writing the p's all over again because I'm just dividing them by 1. Now we have to be a little more careful. Watch very carefully. I'm going to divide 1 by 2. If I divide 1 divided by 2, I will get 1 half. Agree? Next one. I need to do 2 divided by 2. But what is 2 divided by 2? That's just 1. So I'm not going to list that again. Moving on. 3 divided by 2 is 1.5. I don't have that on my list. So I'm going to say 3 over 2. Last number, I need to do 6 divided by 2. 6 divided by 2 is 3. And I already have that listed. So I'm not going to write that twice. So I am done with my list. Let me just get rid of these circles, because I don't want anybody to get confused. Okay, so I'm done with my list. This is how you come up with a list of potential or possible rational zeros for this polynomial. Now, how many numbers do I have? I have 1, 2, 3, 4, 5, 6 times 2. Why am I saying times 2? Because of the plus or minus sign. I have 12 possible rational zeros. And you know, this is just a third degree polynomial. So I know I'm going to have 3 zeros, and who knows, maybe all 3 of them are on my list right here. But these will give us a starting point. And how would you check if one of them is an actual zero? You will perform a synthetic division and see if the remainder comes out to be 0. So you are going to sit here and do 12 divisions to see which one of them gives you a remainder of 0. If it gives you a remainder of 0, then hey, we found the rational zero. But I'm not going to spend time doing that. I just need to talk about how to come up with this list. But what I will probably do is I will go ahead and use a graphing calculator, because if it's a rational number, it's a real number. I should be able to see it as its x-intercept. But I still need to teach this theorem for some reason. Alright, so let me do one more example, but I want to make sure that you're focusing on the leading coefficient and constant, because sometimes I feel like an evil lady. I want to mix up this polynomial to see if you notice it. Unfortunately, this f of x is all mixed. It's out of order. Okay, let's go ahead and rewrite this in order first. Which term has the biggest exponent? The leading term is x to the third power. Next, I need my minus 5x squared plus 7x, and then lastly minus 10. So, you see what I mean? Because if people are not paying attention, they would have probably used a negative 5 to find q's. But what is the leading coefficient here? Leading coefficient is just 1. Alright, let me start with the p's first. P's are all the factors of negative 1. What numbers divide negative 1? Well, we can start by writing plus or minus sign and put 1, because anything can be divided by 1. 1 will always be on your list. It can also be divided by 2. Can I divide 10 by 3? Nope. What about 4? Nope. Next number is 5. And the last number is back up to 10. So these are the factors of our constant. So these are my p's. Now I need to list all the factors of q. And all the factors of leading coefficient. But this one's super easy because leading coefficient is 1. The only number that divides 1 is just 1. So hey, p over q's will be easy. P over Q's will be just all these P's getting divided by Q. So 1 divided by 1 is 1, 2 divided by 1 is 2, 5 divided by 1 is 5, and lastly 10 divided by 1 is 10. If Q is just 1 plus or minus 1, then P over Q will be exactly the same as your P because we're just dividing by itself. Dividing by 1. So how many potential zeros do I have? I have 1, 2, 3, 4, but considering the plus and minuses of them, I have 8 possible rational zeros. So if I perform long division or synthetic division, we're hoping at least one of them gives us a remainder of 0. But this is how we come up with a possible list of zeros, and this process is called rational zeros theorem.